Alright guys, welcome back. So this will be the last video for gravitational fields. Yay! We're still talking about satellite motion. So here's our dot point. Let's just jump into it. So, now, last video we saw that there was this general sort of formula talking about the orbital characteristics of a satellite, okay? And this ratio that we calculate is equal to gm over 4 pi squared. You can see where that comes from just by rearranging a couple of things. Here's the really interesting thing though, all right? If you know the orbital radius of, planet A and the orbital period of planet A, and you also know the orbital radius or the orbital period of planet B, you don't have to use this at all to work out the fourth unknown quantity, okay? Because what we can do is we can say that, the orbital radius of planet A cubed divided by the orbital period of planet A squared, well, sure, that's equal to gm over 4 pi squared, where m is the mass of the central body. But we can do the same thing for planet B, and we can go rb cubed is equal, over period of b squared. That's also going to be equal to this gm over 4 pi squared, because they're both orbiting the same thing. So really, you can get rid of that entirely, and you've just got this relationship. Okay, so if you know 3 out of these 4 things, you can just work out the fourth thing directly from that. You don't have to worry about the mass of the central body at all. Okay, so you don't actually need to know it. All right, the other cool thing is you don't have to convert units to SI units so long as you keep the units of radius the same and you keep the units of period the same. The period could be in days, could be in weeks, hours, minutes, seconds. Doesn't really matter, right? Because you don't have to worry about mixing these non-SI units with the SI units of mass and big G. Okay, if you've got the orbital radius in kilometers for A, you just work out the orbital radius of B in kilometers. If you know the period of A in days, then you can calculate the period of B in days. You don't have to do any conversions if you're doing this particular kind of analysis, okay? So let's check that out in this question here, all right? So Ganymede is the largest of Jupiter's moons. It's got a mass of blah, 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 and an orbital radius of blah, blah, blah kilometers. Sure, all right. Orbital period of blah, 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 or 7.15 days. Cool. Calculate the orbital radius in kilometers of Europa, which has an orbital period of 3.55 days. All right, so what we're going to be doing is just using this relationship. Okay, so the radius of Ganymede cubed divided by the period of Ganymede squared is equal to the radius of Europa cubed over the period of Europa squared. All right, we're trying to find the orbital radius of Europa, so we're trying to calculate RE. So we get RE is equal to, after a little bit of algebra, the cubed root of RG cubed times TE squared over TG squared, okay? And like we just said, the cool thing is you don't have to use SI units when you're doing this kind of question, all right? You can leave things in kilometers because you're trying to work something out in kilometers, all right? You don't have to convert the periods into seconds. You can leave them as days, okay? And that just might save you a little bit of time so you don't have to waste time converting. So if you just pop those values in as they're given, okay, so cube root of, all right, what do we got? 1.07 times 10 to the 6 cubed. Now here's something really important. Don't forget to cube that R, okay? Just be careful. Multiplied by the period of Europa, which is 3.55 days, squared. Okay, don't have to convert it to seconds. So long as all of the quantities for period are in days. All right, so that's why we have to put 7.15 days squared down the bottom for the period of Ganymede. All right, so time is in days for both of those things. This distance here, RG, is in kilometers, which means the distance that we calculate will be in kilometers. All right. And you end up getting something around 6.71 times 10 to the 5 kilometers. Okay. Now you can, of course, convert everything into SI units if you like. If that just makes you feel more comfortable, if it will help you sleep at night, sure, go for it. Okay, it will still work. I'm just saying for a question, for this specific type of question where you're just comparing the orbital characteristics of two things without any mention of the central mass, you can use whatever units you like. Okay, so long as the units for both of the radiuses in the same thing and the units for both of the periods are in the same thing, then you can just use whatever you want. All right, cool. All right, last thing. So, geostationary orbit. So a geostationary orbit is an orbit where the satellite remains directly above the same point on Earth as the Earth rotates. Okay, and it has, if you think about it, the only way that that could be the case is if it was directly above the equator. Okay, it's a bit hard for me to draw this, so if you want, I can sort of show you next time we're in class. But I can try and draw a picture from like the side of Earth. Okay, so here's the Earth as seen from the side. So imagine there's the poles and the equator is going around like that. Okay, now let's say, because the Earth, say, might be rotating, you know, that's a bit hard to see. It's sort of like, who cares? It's just rotating on this axis. Let's say you want some satellite up in space to be above this point here as the Earth rotates, okay? And let's say that satellite's going out to this distance, all right? Think about the path that this satellite would have to take in order to remain above that spot. Like if that satellite was connected with a stick or something, yeah? The only way, the path that this satellite would take, well, think about it. It's not orbiting the Earth. It's orbiting nothing. Okay, that's the path that that satellite's going to take if it's trying to stay above that spot. Okay, that's not an orbit. That's just a satellite floating around in space. Okay, so that's not a geostationary orbit. You can call it geostationary, but it's not an orbit. Okay, it's just a, I don't know, a motion of some kind. But now picture yourself on the equator. All right, and you've got a satellite sort of out there. It's going to have to go around the Earth like that, okay? And it's a bit hard to see without, you know, the proper 3D perspective that's going on. But this satellite would be orbiting, if you were to connect that satellite with that spot right to the middle of the Earth, yep, it's orbiting the center of the Earth. So that's why geostationary orbits are restricted to be basically above the equator. All right, and because it's orbiting the same point, because it's above the same point always, and a point will return to its original sort of location once every 24 hours, then that means this satellite is orbiting the Earth once in 24 hours. Okay, so its orbital period is 24 hours. Has to be. Okay, so main things, geostationary orbits directly above the equator, and its period is 24 hours. You can convert that to seconds if you like. That's 86,400 seconds. All right, so let's do a question about this. So calculate the orbital radius of a 3,000 kilogram satellite in geostationary orbit, assuming the Earth has a mass of that. All right, so what do we know? We know we want to know the radius. We know its period. It's 24 hours or 86,400 seconds. That's just 60 times 60 times 24. We know the mass that the satellite is orbiting, so the mass of the Earth. That's 6 times 10 to the 24. Obviously no big G. And, well, we don't really have any other information. We've got the mass of the satellite, but as we know, that makes no difference to anything unless you're trying to work out the force between the Earth and the satellite. Sure, use that mass, but we don't need to use it for anything else. Okay, how do we relate all these four things together? Well, we could just go and use our handy dandy r cubed over t squared equals gm over 4 pi squared. Cool, and we're trying to work out r. So using some algebra, rearrange that. Cube root of gmt squared over 4 pi squared. Plug your numbers in, all of these, and you end up getting something around 4.2 times 10 to the 7 meters. Okay. Now, just so you are aware, this is the every satellite in geostationary orbit is at that radius. They're just at different points on the circle that happens to be at that radius. Okay. You can go on Google and say, what is the orbital radius of a geostationary satellite? You don't have to give it any other information, and it will know that that is the distance, roughly. Okay, might give it as an altitude, so you can just add the radius of the Earth to get this number. But every geostationary satellite currently in orbit is at that distance from the center of mass of the Earth. Okay, it's just how it is. And they're all in the same circle. They're all in the same circular orbit, just at different points on that circle, obviously, so they don't crash into each other. And they're always going to be above the same point on Earth. That's really cool. Okay, that's really helpful for certain applications. If you need some kind of satellite to be above a location all the time for communication purposes or something, that's really cool. All right, anyway, that's it. We are now done with gravitational fields. In the next few series of videos, we're going to be looking at the other types of fields, which are the electric field and the magnetic field, and applications of both of those. Anyway, I'll see you next time. For now, just relax and take things easy. See you then.